Okay, so we're going to continue today with our work into special relativity, and we're going to deal with simultaneity now. That is Einstein's theory that simultaneous events are also a relative concept, just like velocity is. So let's take a situation where we have two things occurring for two different people, two events, and we have a train traveling in the right-hand direction, and we have a person standing on top of the train. And we also have a person standing on a platform at the train station, and we also have two light bulbs, one light bulb here at the front of the train, in the back, and at the front. Now, these two light bulbs will go off at the same time when these two people are aligned vertically. So the light traveling from this bulb and the light traveling from this bulb will in fact reach the observer, this observer here on the train platform, at the exact same time. However, since the train has a velocity, a constant velocity of, let's say, half the speed of light, then that means that when the light bulbs both turn on at the same time, this person will be moving forward some distance before the light from the front light bulb hits them first. So they say that this light bulb here is turned on first, and the one afterwards, which they're moving away from, is turned on second. Why? Because you see, at this point, this light bulb has a further distance to propagate its light than the one in front does. So if you ask the two people, this person says, was this a simultaneous event? And the answer is no. But if you ask this person, was this a simultaneous event? They say, yes, it was. So the bottom line here is that simultaneity is a relative concept. So I just want to be clear here that simultaneity is a relative concept, because this person who's standing on the train, they might actually, since they're moving to the right at half c, at this point here, they might first see the light from this light bulb that they're moving towards, but then at a later point in time, more to the right, they would see the light coming from the rear light bulb and note that one at this point. So notice these are different points and different times that they would experience seeing the light. I'd like to add another couple of examples of frames of reference being relative. Let's take, for example, the concept of like a mind experiment. Let's say we had a spaceship in outer space, and we assume that we can look out the window of our spaceship, and we don't see any planets, we don't see any other stars, so we have no other markers as a point of reference to judge our own velocity. Now, question, can you tell if your velocity is 0 or if your velocity is some value? It doesn't matter what it would be. It could be anything. I'm just putting a value in here just as an example. Well, my point is that ask yourself, are you able to determine the difference between moving or not moving? Okay, so or no motion. And that's the question. If you can't see anything else, are there any experiments that you could do inside the ship, or even you could even, if you have things inside of the ship, you could place them outside. It turns out that you can't actually do anything to try and figure out whether your velocity is 0 or some value greater than 0, because there's nothing else in the universe to compare your position to. In other words, if there's no other planets, no other stars, all you see when you look out the window is darkness. So now let us consider the concept of having another spaceship, moving towards us. Now in this case, ask yourself, is it, let's call this spaceship A and spaceship B. Now let's say we are in spaceship A. Is there anything that you can do to determine that you are moving towards spaceship B? Or is spaceship B moving towards you? Now what you do know is that the two spaceships are coming closer together, but you don't know which one is doing the moving. And in fact, there's no way to tell. So the reason why this is so difficult is because, remember, we're only dealing with inertial frames, not acceleration. So without acceleration, you can't tell the difference between 0 velocity and some velocity greater than 0. Why? Because in English, it only makes sense to differentiate 0 velocity and something greater than 0. But in fact, they're the same thing. There's no way to differentiate the two. It just depends on who the observer is. So this is like a classic mind experiment that you can try, and it's sort of a fun thing to do. By the way, as a side note, ask yourself this. If this spaceship didn't exist, if you don't have spaceship B, and you only have spaceship A in the universe, and you're in the spaceship, ask yourself this question. Where are you? Can you answer that? Obviously you cannot, because your location could only be defined in terms of another location. And if there is no other thing in the universe to relate to your location in the universe, then you cannot say where you are. In fact, even the notion of you being in a particular place has no meaning, because let's assume you were in a different place in the universe. How is that place any different than the place you were before? It's not. It's exactly the same place. So, because there's nothing else in the universe other than your own spaceship. So therefore, in a way, you may argue, you might say, well, if all places in the universe are the same as any other place, then instead of saying I am at one location, maybe you could even say I am at all locations, because a location has no meaning anymore. So those are cool things to think about in this unit. Now, let's take this another step further in terms of who views something. Let's go back to 0 velocity and some velocity greater than 0. Let's not take something so complicated as or so esoteric as something where you have a spaceship and there's nothing else in the universe. Let's just take the simple concept of the Earth. And you're circumnavigating the Earth, going around it in a little airplane perhaps. And little airplanes are kind of hard to draw. There we go. And this airplane takes 24 hours to circumnavigate the planet all the way around. So it starts here and it goes around and then it gets back to the same location 24 hours later. Now, if you ask someone standing on Earth, is the plane moving? They say, yes, the plane is moving very fast. You ask someone inside the plane, you say, is the plane moving? Now, they have windows, so they can look outside, they can see the Earth, and they can see the Earth moving past, they can see them moving around the Earth through the window of the airplane. And of course, the passengers say, yes, the airplane is moving. Now, we know that the Earth actually, the Earth itself is rotating once every 24 hours. That's called one day. So what if we simply had the airplane, and instead of thinking about the airplane moving around the Earth, now you say, what if the Earth spins underneath the airplane as the airplane just sits in a particular point in the sky? Now, if we had an observer observing this from outer space, now when they see the airplane, they would report that the airplane's velocity is, in fact, 0. Because all they see is the Earth spinning underneath the airplane. Now, from the perspective of a person on the Earth, well, we know that's very different. As before, they would say that the plane is moving. So all I'm trying to do here is explain that the concept of velocity is a relative one. Some people may report a velocity of 0, while others report a velocity that might be much greater than 0. And who's right? Well, they're both right. Because one of the postulates of special relativity is that there is no specific frame of reference that is better than any other. Remember the ether analogy. Michelson-Morley tried to figure out if there was an ether in the universe that would be the so-called frame of reference that would be the best, because light would be traveling through the ether, but in fact they couldn't find it. And so in Einstein's theory of special relativity, we realized that all frames of reference are equally good as any other one. Remember, these are inertial frames, so no acceleration involved in any frames of reference.